Okay, let's get started. And then please your attendance on Blackboard. So, it's the first, maybe morning class after the long weekend. So, so attendance rate is low as expected. So, uh, so after long weekend, so I believe you are about tired, and I was about tired. Okay. Okay, so what we learned in the previous class, uh, we learned about the latch, right? So latch is the basic logic, of sequential logic. So it's a kind of sequential logic. Then what is sequential logic? What is sequential logic? So, I mentioned that the digital logic has two kinds of logic. So it's a combinational logic and sequential logic. Sequential logic, right? Then the difference is that the combinational logic does not have memory, right? So it's memoryless. So the output signal value is only determined by input signal values. And then sequential logic has memory. So output signal values are determined by states of logic. It means so and the current input values. So I mentioned that the states of logic are determined by previous inputs. So that's why the sequential logic has memory. Okay, so it means that the previous values are used for determining output values. So in the previous class, we learned about the bistable circuit. So it means that so actually I just explained about the sequential logic, and then I mentioned that sequential logic includes memory, the memory component, right? So actually the bistable circuit is memory, right? So the output values like Q and Q bar. So you can find the two output ports here. But so so in the bistable circuit, the output values are just maintained, all right? Because I mentioned that there are two drivers, inverters. So and then inverter is driving output values, right? So and then these output values are just maintained, right? So this is memory, but so in the bistable circuit, we cannot find any input ports. So which means we cannot control the values stored in the bistable circuit, right? So this is bistable circuit, okay? So researchers developed latch, okay? Then the basic the so in the previous class, we learned about the SRH, and the SRH includes NOR gate instead of NOT gate. So I already explained that. So actually, we can implement NOT gate using NOR gate or NAND gate. So it means that we can also implement SRH using NAND gate also. Okay. But so I explained about the SLH implemented using NOR gate, right? So in the SLH, they can find the two input ports, so R port and S port. And then I mentioned that the R represents reset, and then S represents set. So also you need to so remember that. So this the circuit set means that the makes output 1, and then reset makes output 0. Okay, so you can understand reset signal and set signal of this SRH like this. So we will also learn about the reset signal in this class. Okay. So so in the SRH, so SRH has two input ports, so we can consider four different combinations of input values, right? Because there are two input ports, and then this is the logic. So actually, so we can think about the four different pieces of input combinations, right? So and then we can analyze this circuit using these four different input combinations, right? So it's S is 1 and then R is 0. So you can estimate that if S is 1, then it's set. It's a set signal. So we can just estimate that we can just expect if S is 1, then Q will become 1, and then Q bar is the inversion of the Q. So it's a 1 and it's a 0. Then why? So we can just analyze the circuit, right? So it's S is 1 and R is 0. So this is 1, and then you know this is the NOR gate. So one of input of this NOR gate is 1. Then the output is always 0, right? It's always 0. Why? Because this is NOR gate. So if this is the OR gate, then our output will be always 1, but because this is a NOR gate, so output is always 0. And then how about the R equals 0? If the R equals 0, then it is equivalent to NOT gate, right? So you can find that this is 0, so actually the output of this OR gate is determined by this signal, the another input, right? But this is NOR gate, right? So actually you can find the bubble here. So if the R is 0, then this NOR gate is equivalent to NOT gate. So what is this input? What is this input? This input is actually 0, right? Because it's 0. Right. And then 0 is the input of inverter, right? So Q will be 1, right? Because so this looks like the 1, 0, and then 0 is inverted, so Q will become 1. So if the S is 1 and R is 0, then the output of this SRH is always 1, right? So Q is 1, Q bar is 0, right? So this is set case. Then S is 0 and R is 1. So we can analyze this circuit similarly, right? So because the R is 1, then this is always 0. So, you know, this is a NOR gate, right? And then because S is 0, so this is the NOT gate, right? So Q is 0 and then Q bar is 1 because Q is connected to this NOR gate, but the one of input of this NOR gate is 0, so this is inverter, right? So Q bar becomes 1 and Q becomes 0, so it's reset. Okay, so we can control the output. So we can control the value, the output value of this SRH using two inputs, S input and then R input. Then, so this is, we can find the answer here. So then if the S is 0 and R is 0, then, so you know, so I mentioned that this is a NOR gate and then one of input of this NOR gate is 0. Then it is equivalent to NOT gate, right? So It means actually if the R is 0 and then S is 0, then SRH will be equivalent to bistable circuit, right? So because this is uh, this is inverter, right? And this is also inverter because S is 0 and the R is 0. And then two inverters are connected to each other. So it's a cross-coupled and then it's connected to each other. So this is bistable circuit. And then I already explained that we can store our values, the output values in bistable circuit. So this is just memory, okay? Because we can store some values in the bistable circuit, so it means it's memory. And then also I explained that actually the internal memory, so not DRAM, we can implement the internal memory of the chip using this cross-coupled inverter, like bistable circuit, right? So it's just memory. So we can just store the value inside of this latch. Okay, if S is 0 and R is 0. If the S is 1, the R is 1, so what will happen? So if it is a 1, then it's 0, and it's 0, 1, it's a 0, and then it's connected to the also the inverter, the it becomes 1. So actually, if the S is 1 and R is 1, then the circuit, the SRH becomes unstable, right? Unstable. So this is the invalid state because the circuit is unstable. Why? So as I mentioned, so the Q is 1. Let's this. So Q is so it's R. So if R is 1, then Q becomes 0. But it is driving the Q. So this is just inverter. So Q bar is also 1. So Q is 1 and then Q bar is 1. So this is the invalid state because so Q bar is just Q bar, the inversion of Q. So the output will be changing continuously. It is swing. It is swing like the some pulse, the electric pulse, but it means it's invalid state. So because we cannot control the behavior of this logic. Okay. Also, and logically, this is also invalid because Q is 0, so Q bar is so Q and Q bar has the same value, so it's invalid. Okay, so we need to avoid this input. So S is 1 and R is 1. Then we need to avoid this input combination. Okay, so this is the behavior of SR latch. Then so SR latch. SR of this SR latch stands for set reset latch. As I mentioned, S represent set, then R represent reset. And then if the so S is 1 and R is 0. So actually, so SR latch have 3 valid input combinations. So 3 valid input combinations. So SR, so which means S is 1 and R is 0. So this is it makes Q1, right? Output 1. So because it's a set piece, and then it's a reset case, so R is 1 and S is 0, then Q becomes 0. And then memory state, so it means that S is 0 and R is 0, then the values, the Q values is stored. It's maintained inside of SR latch. So it's a memory, it's a maintained. I mentioned the value is maintained. So we can store a certain value. Also, we can control the output value using S input and R input, right? So we can change the value, and then after we change the output value, then we can for this changed value inside of SRH, right? And then we need to avoid invalid state, right? So because if S is 1 and R is 1, then the circuit, the SRH becomes unstable, right? So this is the symbol of the SLH. So you can find the R input port, and then S input port here, and then Q and Q bar. Okay, so there are two output ports, but it represents the Q and Q bar, the inversion of Q. So this is SLH. Okay, and then we can also develop. So we can develop the different type of latch. Okay, so it's called D-latch. So it's called the D-latch. Then D-latch has two input ports. The one of the input is clock. This is called CLK. So it is called clock. Okay, and then another input is D. So it is different from the SRH. SRH has two input ports. So it's an S port and the R port. And then it means that the set input and then reset input. But in D-latch has also two input ports. So but the meaning is different. So two inputs are clock input and D input. And then we can define the behavior of this D-latch using these two input ports. How? So the clock. So clock input controls when the output changes. Okay? It controls when the output changes. So the output value, so behavior of this D-latch is determined by clock signal. So clock is the control signal. So D represents the data input, right? So because of this D data input, so that's why the name of this input port is D. So it controls what the output changes to. So you can understand the D-latch like this. So the clock signal is the control signal and D is the just data input. And if the clock is 1, then the output Q becomes equivalent to input D. So D passes through to Q. So what does that mean? D passes through to Q. So it is just equivalent. It means that Q is D. Okay? It's equivalent. But if clock becomes 1, if the clock is 1, then Q is just equivalent. It's a transparent, just equivalent to input signal D. Otherwise, if the clock is 0, so I mentioned that the clock is the control signal. So if the clock is 0, then it works like the memory. So what is the memory? The memory means the data is maintained inside the circuit. So Q holds its previous value. So it's equivalent. So it's actually it's equivalent to the S is 0 and the R is 0 for SRH. Right? So if the clock is 0, then it is equivalent to S is 0 and then R is 0 in SRH because it is memory state. So it's a memory state in SRH. So it's the same. So if the clock is 0, it means that this D latch maintain this previous Q value. Okay, it's same to the memory state of SR latch. And how about the clock is 1? So if the clock is 1, then Q equal D. So, and then, so D can have two different signals, right? So, this is the digital signal, so 0 and 1, right? So, if the clock is 1 and if the D is 0, so if the clock is 1 and D is 1, now this is equivalent to S is 1, R is 0, because the Q becomes 1, right? If the clock equal 1 and D equals 0, then it is equivalent to S is 0 and R is 1, right? Because it resets state in SRH. Okay? So this is a different type of latch. It's called the D latch. Then also you need to memorize the definition. So definition of this D latch. Okay, so D latch has also two input ports, and then so using this clock signal, then we just change the behavior of this D latch. Like if clock is 1, then D pass through to Q. It's transparent, right? So it's a Q becomes D. Q is equivalent to D. And then if the clock is 0, then this is memory state. So Q holds its previous value. Okay. And then I also explained that so equivalent SLH state based on the clock and D. If the clock is 1 and D is 1, then it is equivalent to S is 1 and R is 0 in SRH. The clock is 1 and D is 0, and it is equivalent to S is 0 and R is 1 of SRH, and this is the memory state. So why did I explain? It is because we can implement the latch using SRH. So actually we can implement the latch using SRH like this. So as I explained, so you can find the SRH here, okay? And then if we just add inverters, so this is inverter here, and so we just add the to AND gate, so we can make the D latch. So we can just generate the truth table like this. So if the clock is 0, so this is the memory state, right? So for the SRH, S needs to become 0, and then R needs to become 0. Okay, so SRH is here, and then actually E bar is also unknown. So in the truth table, the D is unknown, so don't care. And then because D is don't care, so we don't know the exact value of E bar. But regardless the value of E, if the clock is 0, then it's the memory state. So it's the Q is equivalent to Q previous value. This is the Q bar previous value. So it's the memory. Okay. So if you see this circuit, then if the clock is 0, so it becomes 0 and 0, and then the one of input of AND gate is 0. So obviously this is 0 and this is 0. So that's why. So if we just add this circuit in front of SI latch, then we can make R0 and then S0. So we can make the memory state, right? And then the clock is 1 and D is 0, then D bar is 1, right? So in this circuit, the clock is 1, right? And then D bar is 1. So actually, if the on-off AND gate, the on-off input of AND gate is 1, then it is equivalent to A. Then it is equivalent to A equal Y. Right. So obviously, so actually, so this is the E bar, and this is D. If the clock signal is 1, right? So because so actually R is connected to D bar, so it becomes 1, and S is connected to D, so S becomes 0. So what is this? This is the reset state. Reset state of SRH. So Q will become 0, Q bar will become 1. So if you see this truth table, then Q is equivalent to D, right? And then it's 1, 0, and it's you know, this S becomes 1, R becomes 0. So Q becomes 1, and then Q bar becomes 0. So because this is the set state of SRH. So actually Q is also D. So actually we define the different latch logic called D latch, right? But we can implement this D latch using SR latch. So you can just memorize. You can just memorize the definition of this T latch. Okay. So based on the clock signal, this T latch can be transparent. So which means that Q is equivalent to D. And if the clock signal is 0, then this D latch just store the previous value. It's a memory. Okay. Then we can just implement the D latch using basic logic gates and SRH. Okay. So this is answer. Okay. Then so we can also implement the latch using system value. So in the previous class, I explained about the always on the bar latch. Okay, it's always a statement, and then I mentioned that we can use always on the bar latch for implementing latch. But I mentioned that it's kind of a bug, but sometimes it's a very rare case. In a very rare case, we may require to implement latch, like some very specific logic, like some memory controllers. But just think. So actually, in the normal digital logic, we seldom use. We seldom is not. We do not. We do not use latch in normal digital logic. But anyway, our system value supports the latch implementation using always on the bar latch. Okay, so you can so this is the example always statement for latch. It's actually the latch. So let's see the system value statement. So you can find that if clock is true, so which means if clock is 1, okay, it's equivalent to clock is 1, right? Then Q becomes D. Q is equivalent to D, right? How about if clock is 0? you cannot find. So actually in this statement, we cannot find if the Q is 0. So which means we cannot find any else. We cannot find any else statement in this latch implementation. So always on the latch. So why? So we actually we should just store the previous signal, right? So which means that the Q signal is not changed, right? If the clock signal is 0, then Q is not changing. It's a memory state, right? So we don't need to define this behavior in the system variable, right? Just Q is maintained. So I explained that the always statement will be executed if the input signal. So actually the sensitivity list is not defined here, but you can understand like this. So always at a star sign, so it means everything. But if we use the always statement like this, then always statement just make the sensitivity list automatically using input signals. So actually what is the input signals for this statement? Clock and D. Okay. So if the clock or D signal is changed, then this always statement will be executed, right? But actually memory state, the output is not changed. So even though the input signals are changed, the output signal is not changed, right? So we don't need to define the output values for clock is 0, right? So we want to implement latch, right? So in the memory state, if the clock is 0, that means it's a memory state. So output is not changing. So actually, we don't need to define this case in the always statement because output is not changing. Okay, so this is the always statement. So we do not use as here. So it means inside of always statement, so always on the comp, and then if we do not use else statement, then it is equivalent to latch. Okay, so in this always statement, the else is not defined, or otherwise S is not defined, so it means the clock is 0, then latch will be generated. Okay, so it's the same inside of always underbar comp. So we can use this always underbar comp for implementing combination logic. But if we do not define else or otherwise, so like default in case statement, then that should be generated, and then it's bugged. Okay, so in order to implement the latch, then we need to use the always on the latch inside in system value. Okay, so otherwise the system value will generate warning sign or error sign. Okay, so this is the example. So the latch implementation in system value. So I believe you can easily understand the behavior of latch using this statement, right? Okay. Understand? Okay. Then we will learn about the flip-flops. Actually, this is very important. So so I mentioned that in normal digital systems, we do not use latches. Okay, so latches, if the latches are implemented or generated by system value code, or some this the system code, then that means bug, right? But we frequently use flip-flops. Okay, we frequently use flip-flops. Then why? Why did we learn about the latch? So it is because we can implement flip-flops using actually latch. Okay, so that's why we first learn about the latches, and then we will learn about flip-flops. So firstly we learn about the bistable circuit, and then actually the latch. Then the latch has the input port because we cannot control the output of a bistable circuit. And now we will use flip-flop, but we can implement the flip-flops using latches. Okay. Let's learn about the deep flip-flops. So you can find that this is the flip-flop. It's not latch, but it's D. Okay, so we just learned about the D latch. Okay, as you can see, D flip-flop has two input ports like clock and D. Oh, it's the same. The inputs of D flip-flop are the same to the input ports or input signals of D latch. Okay, so it means actually the meaning can be similar. Okay, so clock is also the control signal, and then D is the data input, like D latch. But the behavior is different. How? This is the function of D flip-flop. So you can find that the D flip-flop samples. So what is sample? What is sampling? So sampling means that at a certain time, it's a very short time, so t equals certain time, like t0, and then if we just store a certain value of input, so this is the input, but we just monitor the input value, but at a certain time, like t equals t0, and then if we just store this input value or input state, then it means we sample. It is the meaning of the sampling. So it means we sample input signals. We sample input values. Okay. So this is the meaning of sampling. So sampling means that at a certain time, it's a very short time actually in our real world. So during the very short time, we just store a certain value. This is the meaning of sampling. So if you see the behavior of the D flip-flop, you can find the same. It samples D is the input, the data input, when on rising edge. On rising edge of clock. So what does that mean? So actually this is the clock signal. Okay. So clock signal will be changed like this. So this clock signal is also the digital signal. So the clock signal will have two different values, 0 and 1. So rising edge means that if the signal value changes from 0 to 1, then it is called the rising edge. Okay, this is the rising edge. So inversely, if the value changes from 1 to 0, it is called falling edge. Okay? So the definition of D flip-flop flip-flop samples D on rising edge of clock. Okay. So it samples. So you can find the symbol of the D flip-flop. Actually, the port of the D flip-flop is same to the port of D latch. So as I mentioned, the D flip-flop has the clock port and D port, but you can find the different signal here. Okay, so the D latch, so we cannot find any triangle signal on this clock port, but for the D flip-flop, we can find the triangular signal, triangular shape on the clock port. It's different, but it has some same port. Okay, so but the meaning is different. So actually, if the clock rising at the right on the rising edge of the clock, then the Q becomes D. Okay, so it means actually the D flip-flop is transparent only on the rising edge of clock. Okay, in the D latch is transparent, so it means that the Q is equivalent to D when the clock is 1, right? But for the D flip-flop, the D flip-flop becomes transparent only on rising edge of clock. So it's a difference. That's just the difference between D flip-flop and D latch. Okay? And otherwise, it's a memory state. So previous value is just maintain inside of D flip-flop. Okay? So during the very short time, it's a rising edge. D flip-flop becomes transparent. So Q becomes D. Otherwise, D flip-flop just store previous value. Okay, so it's a different. So because the D flip-flop samples the input signal D on rising edge of the clock, so it's called the edge trigger. Okay, and then actually the clock signal looks like this. So clock signal. So clock signal is a very specific signal. So it controls the behavior of digital circuits. And then, so this is the typical behavior of clock signal. So you can observe that for the clock signal. So clock signal is actually periodic signal. Okay, so which means that the values of clock signal changes periodically. Okay, so as you can see, you can find that the 1 and 0 are repeated. So periodically changing. Also, it means the period. So this is called the period of the clock. So T. So clock is the periodic signal, so T is constant. Okay. So this is so the time gap between this rising edge to the next rising edge is called the period of clock, and then this period is the constant value. So this is the clock signal. So you can just understand the clock signal like this. The period signal, and then we can define period of this clock signal. Okay. Actually, the inverse of period is the frequency. So when we buy a CPU, right? So maybe the smartphone, so like the Exynos or Qualcomm Snapdragon, so we can just we can find the clock frequency, the maximum frequency. The frequency, it means this one. Okay, so this is the inverse of period. Inverse of clock period is actually clock frequency. Then we use this clock frequency value for estimating, just estimating the performance of processor. So for example, my smartphone has the Exynos, and then the clock frequency is like kind of 2 gigahertz. And then your smartphone has the Qualcomm Snapdragon, and then the clock frequency is kind of 1.5 gigahertz. So which is better? So we can think that the Exynos is better because clock frequency is higher, right? So that is this one. Okay. So I will explain later why the logic or the signals use clock signals. Okay. But you need, so that's why deep flip-flops are so very important, very critical logic, very critical basic logic for digital systems, for sequential logic. Okay. Then how can we implement the deep flip-flop? So we can implement the deep flip-flop like this. So what can you observe? So we can observe that in order to implement the deep flip-flop, so D latch. So this is the symbol of D latch, right? Because we cannot find any triangles on the clock port. So if we just connect the latch back to back, it's a serially. If we just connect two the latches back to back, and clock signals is connected to this back to back the latches like this. So you can find that for the second, the L2, the latch, the clock signal is just connected, and for the forward the latch is L1, the clock signal is inverted. Then we can implement the flip-flop. How? So we learned that if the clock is 1, the flip-flop is the latch is transparent. And then if the clock is 0, then the latch is opaque. It's memory, right? And then based on this behavior of the latch, we can analyze the behavior of the flip-flop, right? So if the clock is 0, then this is 0, and then this will become 1 because it's inverted. The clock signal is inverted. Then, so the clock is 1, the latch is transparent. So this the latch is transparent, and the latch is opaque. Okay, it's a memory. So what will happen? If this is 1, then N1. N1 is equivalent to this D. Okay, so input D. But this L2, because this L2 is opaque, the Q is not updated by this D. So N1 just holds the N1 is just equivalent to the is D. So N1 is D, is the same, but Q just store the previous value if the clock is 0. Okay. So it is apparent, transparent. Then what will happen if the clock signal becomes 1? If it becomes 1, then it's 1, and then this is 0. So this becomes opaque. Then it becomes transparent. Okay, L2 becomes transparent, and then the L1 becomes opaque. But we already saw, which means D cannot be transferred to the this N1 because it's a memory state. Okay, so this value is just maintained even though the value is changed for this input D. Even though the value is changed, the N1 maintains its previous value, right? Because it's a memory state. But it's transparent. The L2, the second D latch is transparent, so Q becomes N1, right? So it's a clock 1. So if we just combine these behaviors, then when the first D latch is transparent, the N1. So it's a clock signal change like this. Okay, so here. So for this period, if the clock signal is 0, then it's transparent. The L1 is transparent, which means the input values, this input value is just transferred until N1. The N1 is just equivalent to this input signal. But when the clock signal is changed to 1, then it is closed, it's opaque. Then this signal is transferred to the Q. So what does that mean? At this point, L1 is closed, and then this value is transferred to the N1. So what does that mean? At the rising edge of the clock, this input signal, on the rising edge of signal, this D input is just transferred. Do you understand? So by connecting the D latches back to back, so we can implement the flip-flop, D flip-flop, and then you can just analyze this circuit like this. So I just start from the behavior of the latch. Okay, so clock is 1, then it's transparent, and clock is 0, and it's opaque. And then if we just combine the behavior of the latch for this D flip-flop circuit, then we can understand the behavior of D flip-flop. Okay. So actually, for Korean students, 이게 좀 너무 오래된 거 동대문 말잖아요. London Bridge song, you know? So it's a London Bridge song. Is actually in Korean, it's kind of 동대문 song. 이거 동대문이라는 말. 그런 비슷한 거예요. It's similar to the London Bridge, right? The kind of 동대문 song. For the D latch is we just open the 동대문, the gate, then it's transparent. Okay, the signal is just connected. if you don't close the gate, then it's kind of a memory state, right? And then by combining this behavior, then we can make the flip flop, right? 해볼성 다 알죠? 내가 너무 오래된 건 아니죠? 네. Okay, then let's see the behavior. Let's compare the behavior of the latch and the flip flop. Okay, so actually, the symbol is very similar, but do not be confused because the flip flop has this triangle shape on the clock port. Okay, so and then so this is the clock signal. And then so actually it's a different, but so clock signal is also changed, and then this is also input. So it's an input port, and then we can just compare the latch, the output of latch, the latch, and then the flip flop. So then let's think about the latch. So how can we figure out the output of latch based on this waveform? So we can just apply the kind of 동대문, like transparent and opaque of the opaque state of the latch. Okay. So for the latch becomes transparent if clock is 1. So it is transparent if the clock is 1. Also, it's transparent. So transparent, it means the output is equivalent to input. So which means during this period, if the clock is 1, then actually the latch output of latch is equivalent. Then how about this period? Its clock is 0. It's memory, right? So it's maintained. Okay, it's just maintained. We don't need to consider this value. But this value, this value is just maintained. How about this period? It's a transparent because the clock signal is 1. So actually it is equivalent to this signal. Okay. So it's equivalent. Just equivalent. Okay. And then here, so this is clock is 0 and this is opaque. So we don't need to consider input. Just this previous signal, the previous value is just maintained. So it's maintained. Okay. So it's a transparent also. It's right here. So we can understand the behavior of the latch like this. Okay. Then how about the flip flop? So when we understand the behavior of flip flop, actually we need to focus on the rising edge only. Okay. So deep flip flop is just transparent only on the rising edge of clock. The different. The latch is transparent if the clock signal is 1. But deep flip flop is transparent if on the rising edge of clock. So just this period, this time. Okay, so how? So here, then, so this is the output. So at the right edge of clock, D is 0, right? So it's 0. And then this value is just maintained. Okay, so just 0 is maintained. And then we need to check this point because this is the rising edge. So at the rising edge of clock, on the rising edge of clock, what is the value of D? D is 1. So it is changed to 1. Okay? Then it's maintained because it's opaque. So it's maintained until the rising edge. So what is the value of D? Oh, D is 1 at the on the rising edge of clock. So it's 1. It's updated, but because the value is the same, so the waveform is just maintained. Okay? So as I mentioned, you can understand. You can understand the behavior. You can differentiate them. You can understand the behaviors of flip-flop and latch. The flip-flop, the output is transparent on the rising edge, on rising edge of clock only. Okay, only on the rising edge of clock. Otherwise, the value is maintained. Latch, the output is transparent to input while the clock signal is 1. Okay, that's different. You need to understand this. Okay, so this is very important. Actually, so every distance system includes deep flip-flop. Okay, as I mentioned, so the CPU is also kind of deep flip-flop. Kind of distance system. So which means the CPU also includes many deep flip-flops. Okay. So you can understand the behavior like this. Okay, so this is answer, right? Actually, but if you see that this real, so the real waveform of this D latch and then D flip flop, you can find that. So actually, you can find some delay. Okay, so because so when I explain about the waveform, the behavior of this D flip-flop and the D latch, so I do not consider delay of the circuit, but actually, so as I mentioned, the circuit runs in the real world. So actually, we can observe some delays. So that's why you can observe some delays between the input and output. But here, okay, but you can just understand that actually for the flip-flops, you need focus on edge only. So flip-flop is transparent only on the edge of a clock, rising edge of a clock. Then for the latch, it's transparent to the clock if the clock is 1. So that's why we can say the latch is the level sensitive. It's a level sensitive. Okay, so which means that we can just check the clock level. So if the clock is 1, then flip-flop is edge sensitive. Okay. So we can say that the latch is level sensitive. So if the clock is 1, it's transparent. Flip-flop, it's edge sensitive. So it's a rising edge of clock, it's transparent. You can just understand like this. So then how can we implement the flip-flop in system Verilog? So in order to implement flip-flop, then we need to use the always on the bar FF. So FF represents the flip-flop. So flip-flop. Okay. So that's why we use FF in the system Verilog. So if we use the always on the bar FF, then we can implement the flip-flop. But if we use always underbar FF, then we need to also define sensitivity list. So actually this is the implementation of B flip-flop. So as I mentioned, I use arrays underbar FF, but we can find sensitivity list. Sensitivity list will start using this S sign. Okay, then this is the sensitivity list. So as I mentioned, if the condition of sensitivity list is true, then this always statement will be executed. Then what is the condition? What is the condition of sensitivity list? The condition COSE221. So it means the positive edge. Okay, so positive edge is actually equivalent to rising edge. But in system Verilog, we use plus edge. So it means the positive edge. Yeah. We can also define the negative edge. So negative edge is the falling edge. Okay. So in this example, we define positive edge of clock. So it's a rising edge of clock in the sensitivity list. So what does that mean? It means this always statement will be executed on positive edge, on rising edge of clock. Right? Then what is the behavior? Behavior is Q is equivalent to D. It's the same. So as I mentioned, the flip-flop is only transparent on rising edge of clock. So, this already underlying effect statement will be executed on rising edge of clock because of the sensitivity list. And at this time, Q is equivalent to B. The Q is transparent. Q is updated by B. Otherwise, what is the otherwise? It's memory. So Q value is just maintained. So we don't need to define change of Q. Okay? So this is the flip-flop. Flip-flop implementation in system value. So it's not a problem. So as I mentioned, we frequently use flip-flops in this system. So inside of arrays underbar FF, we don't need to define else state. Okay. So in this example, I just define Q equal P, but it is executed on rising edge on. Okay, so transparent. So as I mentioned, in the digital system, we frequently use flip-flops. So which means we can also use some vector. So like kind of group of flip-flops. So as you can see, so this is the D input, but the width. So width of this D is 4-bit. Okay, it's a 4-bit signal. Then we can just implement the flip-flop like this. So because the Q is just equivalent of D, so the bit width of the Q is a 4-bit. Okay, then you can simply flip-flops like this. Okay, and then this group of flip-flops, the group of flip-flops is called register. Okay, so in so actually in CPU, like processor design, so we frequently use the terminology register. Then actually in registers, we can just store a certain state or values. Okay. So, but you can just understand that register is the kind of group of flip-flops. Okay, so it's equivalent. Okay. So we can also implement the registers like a group of flip-flops like this. This is very simple. So this is the 4-bit signal, D and Q are 4-bit signals. Then actually it's the same. Q is equivalent to D. That means that is the 4-bit register. Okay. Okay. So and then so using the flip-flop, then we can also define the different type of flip-flops. But it's a kind of enabled flip-flop. So enabled flip-flop has 3 inputs, like clock is the same, D is the same, and enable signal. So enable the flip-flop is that based on this enable signal, then D can the input can pass through the Q on the clock edge. So if the enable is 1, but if the enable is 0, then D is not updated. D is not updated to Q. Q is not updated by D. Okay. So enable the flip-flop just control the pass through like so like the output is updated by input if the enable is 1 on the rising edge of the clock. Okay, because the flip-flop just update the output on the rising edge of the clock. But if the enable is 0, then the previous state is just maintained. Okay, even though the even though on the rising edge of the clock. Okay, so this is the equivalent circuit. Okay, so what can you see? So D is here, and then it is a 2-to-1 mux, and then this is the enable signal, and then the output. The output port in Q is connected to the one of input of 2-to-1 mux. So if enable is 1, then it is connected, the D is connected to the input of a flip-flop. So it's normal flip-flop, right? If enable is 0, then this will not be selected. So what is selected? This will be selected. Okay. So the output is just feedback into the input port of E flip-flop. Okay. So what does that mean? It's maintained. But you may think, oh, this circuit is okay. So when I mentioned about the combinational logic does not include feedback loop, right? So if the combinational logic includes the feedback loop, then this combinational logic becomes unstable. The value changes continuously. Unstable means that the values are changing continuously. Now, how about this circuit? This circuit has the feedback loop from the output to input. So unstable or stable? It's stable. Okay. And then the behavior is just controlled by enable. So sequential logic, like if we use the flip-flop, then this logic can include feedback loop. Even though this circuit includes the feedback loop, this is stable. Okay. So this is the system value implementation of the enabled flip-flop. So what is different? This is included. So if the enable is 1, then Q is D. When? On the writing edge of the clock. Else, it's maintained, so we don't need to define else state. So you can find that there is no else statement here. So it is because the previous value is just maintained. Okay, so if we use already on the bypass, we don't need to use else always. So it's not about. Okay, so just understand like this. Okay, so I will stop here. Any questions? Yeah, thank you for your attention. See you in the next class. 감사합니다.